Good morning, Chem 20s. Our lesson today is going to be on calculating pH and the hydronium ion concentration. At one time, the explanations of acidic and basic solutions were independent of one another. Acidic solutions were explained by the presence of aqueous hydronium ions, whereas basic solutions were explained by the presence of aqueous hydroxide ions. The greater the concentration of hydronium ions, the more acidic the solution is. Similarly, the greater the concentration of hydroxide ions, the more basic the solution is. So let's take a look at the pH line which we mastered in the previous video. If we take a look here, the higher my concentration of hydronium ion, you will notice the more acidic my pH is. The lower my concentration of hydronium ion, and the more basic or the less acidic my solution is. Now, we can think of this in a number of ways, and I want to relate to something that we have previously done on the previous video. So if we take a look at this and we say changes in pH can actually be extremely deceptive, and I understand quite easily why it's so tricky for most students. So let's pretend we have a solution of pure water and we're going to add vinegar to it. So we are going to change the pH from 7 down to 4. This movement of 3 pH units seems like a very small amount in that it's not going to be very significant. However, when you think of it in terms of the hydronium ion concentration, it's going to have a very significant difference. So let's take these concentrations and put them into real numbers. So when I look at pH and it changes by 3 pH values, you would think, well, that's not that much. However, when you think of it in terms of hydronium ion concentrations, we are changing by a factor of 10 to the exponent 3, or 1,000 times larger the hydronium ion concentration is going to be, because it's 10 times larger for each pH value. So it'll be 10 times larger, 100 times larger, 1,000 times larger. So we find this a little bit deceptive as we think our way through it. Again, my hint would be draw a quick pH scale. I think it's a whole lot easier when you can actually see it written down rather than trying to just visualize it in your head. Now, pH has previously been defined as the negative exponent to the base 10 of the hydronium ion concentration. So when we had a pH of 7, it was 1 times 10 to the negative 7. When we had a pH of 12, the hydronium ion concentration was 1 times 10 to the negative 12. This is a great simplified definition, but this is only helpful if pH is an integer and the concentration values are simple powers of 10. If we were to say the pH is 8.45, you could not do this same jump between pH and hydronium ion concentration. And we are going to be given pHs that are like 4.8 and need to express them as hydronium ion concentration. Or we're going to be given a hydronium ion concentration of 7.9 times 10 to the negative 7 moles per liter, and we are going to have to express that as a pH. Therefore, we have to get a little bit more specific with our definition of pH. From now on, we are going to refer to pH as the negative of the logarithm to the base 10 of the hydronium ion concentration. So this is going to be our new formula. pH equals the negative log of the concentration. Remember, square brackets means concentration of the hydronium ion concentration. Well, what I think we should do is let's practice a couple examples. So we have a solution of hydrochloric acid, and it contains a hydronium ion concentration of 2.34 times 10 to the negative 3 moles per liter. We would like to find what is the pH of this acid solution. So using my new formula, pH equals the negative log of the concentration of the hydronium ion. So we are going to take the negative log of 2.34 times 10 to the negative 3 moles per liter. So in your calculator, and we have to hit these buttons exactly. Now, if you have something other than a graphing calculator, you will want to try typing this in until you get the answer that we all have. So your order might be a little bit different on how you type it in, but you will have to play around to figure it out. So negative, and then hit the LOG button for logarithm, and a set of brackets will open up. I'm going to go 2.34 times 10 to the raised negative 3 and close the brackets. And I'm going to hit enter. And the number you should get on your calculator is 2.630784143. I'm going to remind you that pH never has any units, so there's no units on this. Now, the interesting thing about pH is pH has its own rule for significant digits. We previously did not look at this rule because we weren't going to do any pH calculations. So because we weren't going to get any practice, we didn't learn the rule. Now, though, we're at the stage where it's important enough for us to actually know the rule. So here's the rule. The number of decimal places in the pH value is equal to the number of significant digits in the hydronium ion concentration. So when we go to look at this, the number of decimal places in the pH value is going to be equal to the number of significant digits in the hydronium ion concentration. So my hydronium ion concentration was 2.34, 3 sig digs, which means I'm going to be allowed in pH 3 decimal places, which means I'm going to record this number as 2.631 because this 7 is going to round up my 0 to a 1. So I have 3 total significant digits for concentration. Therefore, I'm going to have 3 decimal places for pH. Okay, let's try this again. Pause the video, and this time you try the calculation and also try to put it into the correct number of significant digits. So, example 2. Milk of magnesia is used to treat symptoms caused by too much stomach acid, such as heartburn and indigestion. If it contains a hydronium ion concentration of 2.7 times 10 to the negative 11 moles per liter, we would like to know what is the pH of this solution. So my formula again is pH equals negative log of the hydronium ion concentration. So substituting in negative log of 2.7 times 10 to the negative 11 moles per liter. So to type this in my calculator, negative log, set of brackets opens up, 2.7 times 10 to the raised exponent of negative 11, enter. And my full calculator answer was 10.56863624. So let's remember our rule for significant digits again. And our rule for significant digits states the number of significant digits in the pH value is equal to the number of significant digits in the hydronium ion concentration. So my hydronium ion concentration has 2 total significant digits. Therefore, I am going to be allowed 2 decimal places. So my answer is going to be recorded as 10.57 pH. It's going to round it up to a 7. Okay. Well, this formula actually comes with a problem. given that most of you have little to no experience with logarithms in math to this point, it is impossible for us to take that formula for pH and move it around to solve for hydronium concentrations if they give us pH in the question. Therefore, we have to memorize a new formula because we just don't have experience manipulating a formula that contains a logarithm inside. So the two formulas we could use, although in this room, I find that I'm going to concentrate more on this one, is that in order to find the concentration of hydronium ion, take 10 and raise it to the power of negative pH, or take the inverse log of the negative pH. So I can prove to you that these two formulas are the same. So to take an inverse log, you go second function log, and you will notice that on your calculator, it gives you 10 to the raised exponent. Well, that's exactly what we have here. So these formulas are the same. I don't care which one you use whichever one you can memorize. So let's try another example. A solution of seawater has a pH of 8.31. What is the hydronium ion concentration of the seawater? So we are trying to find hydronium ion concentration. So H3O plus equals, and we have our new memorized formula, 10 to the raised exponent of a negative pH. So we are going to take 10 to the exponent negative 8.31. So in my calculator, how I type this in is I like to go second function log, and that will automatically give me 10 to the raised, and it'll even open up my set of brackets. If you would like to go 10 and then do the little top hat, that is fine as well. So I'm going to type in negative 8.31 and make sure it's a negative. Now, on my calculator, I've got a very long answer, 4.977888194 times 10 to the negative 9, and this is going to be in moles per liter. Because pH doesn't have a value, when I convert back to a concentration will be recorded in moles per liter. So what I would like to do is I would like to remind you of our different little pH rule. And so our interesting little pH rule, if you will remember, says the number of decimal places in the pH value is equal to the number of sig digs in the hydronium ion concentration. So if we know that this is a pH value and it's got 2 decimal places, therefore my concentration is going to have 2 total significant digits. I'm going to say that again. Since decimal places in pH are only considered significant, we have 2 decimal places in this pH. Therefore, we are going to have 2 total significant digits in my hydronium ion concentration. So I'm going to record this as 4.9 times 10 to the negative 9 moles per liter. Okay, why don't you try an example? Copy the question, try getting the answer, and then unpause the video to check your work. So, example 2. A glass of cranberry juice has a pH of approximately 2.4, making it the most acidic of all the fruit juices. What is the hydronium ion concentration of a glass of juice? So to find the hydronium ion concentration, it's 10 to the exponent negative pH. So that's going to be 10 to the negative 2.4. And we're going to type that into our calculator. Negative 2.4. And my answer works out to be 0.00398101717. Again, it's a concentration, so it's moles per liter. I want to remind you that this value up here is a pH. and it only has 1 decimal place. Therefore, when we come down to concentration, we are only allowed 1 total significant digit. So I can either record this as 0.004 moles per liter, or it seems like when we do concentrations of hydronium and hydroxide and acids and bases, we use scientific notation a lot. So I would call this 4 times 10 to the negative 3 moles per liter. Again, 1 total significant digit to match the 1 decimal place on the pH. Now, in order to calculate POH and hydroxide ion concentrations, the formulas are the same as the ones we just did. However, instead of saying pH equals the negative log of the hydronium ion concentration, we're going to replace pH with POH and hydronium with hydroxide, because remember, hydroxide goes with POH. That's our definition from the previous video. So our new formula is going to be POH equals the negative log of the hydroxide ion concentration. Again, when I go to manipulate this, I have to memorize a new formula. So if I want to find the hydroxide ion concentration, similarly as when we found the hydronium ion concentration, we're going to go 10 to the raised negative POH exponent. So this would be my other formula for me. So really, all I have done is I've substituted POH for pH and hydroxide for hydronium ion concentration. Well, let's try 2 more examples. A sample of tap water has a POH of 6.30. We would like to know what is the hydroxide ion concentration. So to find hydroxide ion concentration, we're going to take 10 to the negative POH. So 10 to the negative 6.30. So type that in my calculator, 6.30. And my number works out to be 5.011872336 times 10 to the negative 7 moles per liter. Again, I want us to realize that the rule works exactly the same way. If you think about it as the number of decimal places for pH equals the sig digs in concentration, the number of decimal places in POH will equal the number of significant digits in the hydroxide ion concentration. So the rule for pH and POH is exactly the same. So since I have 2 decimal places for POH, I'm going to have 2 total significant digits for hydroxide ion concentration. So it's going to be 5.0 times 10 to the negative 7 moles per liter. 2 total sig digs, 2 decimal places in POH. Okay, last example. Please try this one for yourself and then unpause to check your work. Ammonia is used in many cleaning solutions. If it contains 1.80 times 10 to the negative 3 moles per liter of hydroxide ions, what is the POH of this solution? So POH equals the negative log of the hydroxide ion concentration, negative log of 1.80 times 10 to the negative 3 moles per liter. So negative log, brackets opens up, 1.80 times 10 to the negative 3, close the brackets, and my answer is 2.744727495. Again, my concentration has 3 sig figs, so that means I'm going to have 3 decimal places. I'm going to record my POH as 2.745. Reminder, no unit on pH. Now, I have a follow-up question on this, and my follow-up question says, Is this solution acidic or basic? Okay, now this is a POH. So my rule I tried to teach you last day was think of this as a pH. If the pH was 2.7, we would all say that this was acidic. However, since they want to know pOH, that means instead of it being acidic, remember pOH and pH are exact opposites of one another. So if the pH of 2.7 is acidic, then the pH of 2.7 is going to be basic. How do I know? I know because the pOH value is less than 7. Now, another reason I can say that I know this is because if I take a look on here, right, pOH value we said was 2.7, so it's roughly here. Well, if we go up, that means my pOH value here. Oh, see, I goofed that. Let's try that again. That was a pOH value that we had. Ooh, I got tricked. Nice, I'm human. So my pOH value was 2.7, so it's right here. So because it's right here, we know that this side of the line is basic, where this side is acidic. So you can draw a pH scale, or you can do what I did on the previous slide, and I pretend it's pH, and then I pick the opposite answer to that.